The best solar cells are about 15% efficient. We're trying to manufacture them at ASU. We've got $35 million for the next 5 years, well, 10 years basically, but 35 for 5 years, to be able to figure out how to make them 40% efficient. This is a real problem. I mean, a real problem with science. It's a great idea. It's a great problem, right? Energy independence, all those kind of things, new technologies, new industries. So we need people that are college and career ready that are going to be able to think about these kinds of things deeply and be able to manufacture new technologies to be able to perfect them and move on. But the mathematics and science is something we can engage kids in right now. We want kids to be college and career ready.
Readiness in mathematics, you have the region, for the state and region, seems to be advancing a bit from year to year, but almost 40% of new Texas students in 2005 required developmental education. So we are advancing, but this has to be a huge concern.
I hear math professors who say, just send me a student who knows that the quantity a plus b squared is not a squared plus b squared. Teach it to them 17 different ways, but when they come into my calculus or pre-calculus classroom in college, I'd like them to know at least a little bit of algebra and have thought about it, rather than be able to do all these different things that are on the state test or on the SAT. The only course that helps you universally is mathematics. The more mathematics you take in high school, the better you do in biology, the better you do in chemistry, the better you do in physics in college.
Would it be possible to make students aware that they're doing the same calculation time after time? Because one of the things that happens is students seem to think that calculating polarity is totally different than calculating density, and the mathematical process is essentially identical.
Mathematizing, I love that word. Mathematics doesn't just appear. You create a mathematics around a problem, okay, cognitively. You try to attach some meaning to things you've learned before. You make up some new ideas that might be plausible. We might call them conjectures.
What I personally would love to see happen is seeing more math teachers use data collection and data analysis in their classrooms. That would help bridge that gap between math and science. It'd be a massive bridge. So as you're looking at these math standards and these cross-disciplinary standards, you're going to see there's lots of overlap with science and math. So, and yes, math tends to be the language of science.
Is the result of the laboratory a surprise to a student? If it is a surprise, those kids do better when they get to college. If they know the answer beforehand, it has no effect on their learning of the science.
Before I have kids do a lab, I ask them, predict what you think is going to happen. And there's research that shows this, where some physics people did interactive lecture demonstrations because they couldn't do everything in the lab. And they had the college students, we're going to crash these two cars, what do you predict is going to happen? The students would have to sketch it out, talk to each other, and then they would actually do it in the lecture hall. And what they found is that those students' performance on exams was higher than the students who didn't do it, not just on graphing questions, but on everything, overall, because they had a deep, richer understanding of what was going on.
Even for demonstrations in science, it's important that students make predictions before the teacher does a demonstration.
When you just give kids a lab activity and say, okay, go ahead and do it, they're like, okay, got it, got the graph, turn it in. But when you say, think about ahead of time what's going to happen and put it down on paper, okay? And then I walk around and look at all the graphs. So for that cooling one, lots of them had it coming down to 0. So I say, well, is it really going to come down to 0? And then some of them would go, oh, no, it's not, because It's not freezing in here, right? So, but if you don't ask them to make those predictions, that doesn't happen. They just collect the data and they just move on.
As opposed to stuff to remember, stuffing the sausage. You want to be thinking about what can people do? What's the real proof? If people can do things, I do care what's in their head. I mean, you want it to be reasonably accurate and useful. But if they can do things to a high degree of sophistication, that to me is a better proof than merely being able to answer questions on a test.
This week, we went to the Louisville ISD outdoor learning area, and they were collecting anything from water samples, looking at the water quality and the drought. They were looking at, they were counting plants in terms of their location relative to the creek. They were looking at designing an irrigation system, looking at water flow. So you had a variety of different topics that were very much cross-disciplinary in nature in terms of math and science, and very much in something that is real world right now that high schoolers can relate to.
And the connections between math and science in the real world are the ones that engage our kids. So when we can give them some real world context to do some math or science, that's what engages them and they have fun.
It was funny, yesterday morning when we went out, there was a lot of grumbling from high schoolers. Of course, they grumble early in the morning anyway. But by the end, they were no longer grumbling. They were active, they were enthusiastic, involved, they were wanting to do, okay, can we go do this? And taking it to the next level. There was a lot of chemistry activity going on, a lot of physics, a lot of math, all kinds of things, and the kids were excited.
Some problems also beg to be organized in a mathematical way and that tie into potential careers, potential further pursuits for students. And those problems tend to be more motivating for students than problems that are, the kind of things that I typically make up. Hypothetical sorts of situations that nobody in their right mind would want to engage in, merely because the numbers add up.
I think one of the most important things is that students try to connect knowledge to concepts that they already understand. I mean, we do that all the time. When I get to something that I don't understand, I think, well, what's this like? Is it like something that I already know? Can I relate to that? Those are things that we want to teach students and teach teachers to teach students.